All right, thanks so much. It's really a great pleasure to be here talking with you guys tonight. So normally when you start a new job, you should sort of be at the job every day, but I've actually been at the KITP since accepting my new position, and it's been wonderful. So we've been doing this program, and it's really a special place, and I thank you guys all for coming out here to see this tonight. So we're going to be talking about the Great Escape. Okay, so here's our cosmic home. Here's the Milky Way galaxy. This is the center of the galaxy, and there's a lot of stars there at the center, which we call the bulge. It's in a kind of spherical distribution. And here we are out in the suburbs, around 8.5 kiloparsecs away, which, you know, is about 27,000 light years away from the galactic center. So it's pretty far. And, you know, if you look at this picture, the Milky Way seems like a pretty, you know, relaxing place. But in fact, at the very, very center of the galaxy, there's this beast. So this supermassive black hole at the heart of the Milky Way galaxy. So let me just talk a little bit. So I'm going to get to that. The mass of that is about 3 times 10 to the 6 solar masses, and I'll show you how we measure that mass. And actually, you know, so I want to encourage you guys to jump in and ask questions. If anything seems confusing or strange, or you want to know more about something, please do. Just jump right in. Yeah. So this is an artist's rendition. So I will actually, in a few minutes, show you a much more spectacular. Yeah, that's right. That's right. But that's great. So you know, black holes have the Schwarzschild radii of this black hole, and it's about you know, sort of a, you know, the solar system about that size. So it depends on the mass of the black hole. But great question. So supermassive black holes, you know, for normal black holes, which are about the size of the sun, so they weigh about 1 solar mass, we kind of know how they form. So you've got a supernovae at the end of a star's life. So, you know, stars evolve, and at the end of their lives, they sort of die as black holes. And these black holes are about as massive as the sun. And we see these supernova explosions all over the universe. And we know about this sort of production mechanism. But for supermassive black holes, which are now 1 million times the mass of the sun to 1 billion times the mass of the sun, we have no idea how they're produced. So this is a major mystery. How do you actually get something? We understand sort of producing solar mass type black holes, but getting million solar mass type black holes is a real mystery, and we don't exactly know how that happens. Now, black holes can feed, so we think about black holes as sort of cosmic vacuums, you know, going around sucking up all the mass that's in their vicinity. And in fact, they're so good at, you know, they have so much gravity that not even light can escape the sort of gravitational rip. And when these black holes feed, so when they are sort of sucking material in the universe, we see them shining. Okay, so accreting supermassive black holes, more commonly known as quasars. And so you might have heard about these objects. These objects have extraordinarily high luminosities, and that luminosity, or that light, is coming from an accretion disk, we think, a disk of material that is surrounding that supermassive black hole. And you have the exchange of, you know, gravitational energy into photon energy. You've got sort of a disk of material. It shines at different wavelengths, different temperatures, and we see that as a quasar. So a supermassive black hole that's feeding is a quasar. And for many, many decades, the only way we really knew about supermassive black holes was via this sort of luminous phase, this quasar phase. And this is just a picture of a distant quasar, or a relatively distant quasar in a nearby galaxy. These are very powerful radio jets that this galaxy is, that this quasar is responsible for producing.
So light doesn't escape from the black hole.
That's right.
So why is there light around it, including that? Because that is being sucked in and spun around.
So the way you can think about this is, imagine you're a gas particle and you're in an orbit around that supermassive, you're in an orbit around that massive object. Yeah, you're being sucked in, but what we're seeing is the material. Basically, what a quasar looks like is a bunch of rings of different temperature, and those like a black body, like the sun, and each of those temperature rings emits a different frequency black body. This inner part, which corresponds to very high energy because we're very, very close to the supermassive black hole, and the energy of that orbit is very high. That's emitting in X-rays. And then as it gets sucked in, it goes faster and faster and faster. That's right.
And they emit the photons at a higher and higher.
That's right. So the energy is characteristic of this sort of, this orbital energy. So that's exactly, what an accretion disk. This is sort of in Santa Barbara. This is one of the kind of centers for studying detailed models of these accretion disks and trying to understand exactly in detail what these look like. So I've given you this very simple picture where you've got a bunch of rings of different temperature. But in fact, once you put this in the context of magnetohydrodynamics and general relativity, there's nuances to that simple picture. But basically, when we look at quasars, we see sort of the superposition of all of those different rings in that very, very luminous material.
And you corrected on the left, that's an artist rendering?
Yeah, that's right. This is an artist rendering, and this is a false color image of M87. So you can see the radio jets, and this is the disk of the galaxy. And this dark stuff here is dust, which I'll talk about in a little bit, because this is a visible plus radio photo. Yeah. Right. So this is now a hot plasma. So that's that's correct. Do you mean as opposed to? Yeah. So this is, you could think of this as a high temperature plasma. So that's right. And there's magnetic fields in there, and so it deviates from this very simple picture because you have to account for various instabilities that arise in that gas as as you get further or closer away to the black hole. Yeah. No, this is great.
My question is, Dan, I asked this earlier, another person involved in discovery of this simple stuff. So you mentioned magnetic field, sort of gravitational field. It seemed to me that, when I was trying to ask whether or not the gravitational field is the center of the galaxy was correct, even chaotic.
So I'll show you actually a movie that'll answer that question, because we've really now, where we have stars that can probe that, we really understand the gravitational field.
You don't know what to expect, because it's in-body, large numbers, the in-body problem.
Right. Well, but actually now we can do really sophisticated n-body calculations. We can even do general numerical relativity, where we're doing GR in the vicinities of spinning supermassive black holes. But I'm going to answer your question in, I hope, satisfactory detail in a few minutes here. But that's a key question. What is the gravitational field at the galactic center? Yeah.
Corollary to that question, when Andrew Gedge was up here describing these black holes, he asked, well, why is this kind of gravitational field? Why aren't the stars that are tracking this how to discover the black holes? Why do we get up here?
Well, so I will also answer that question. Right. And so that has to do with conservation of energy and angular momentum, and so we will definitely get there. This is great, though, guys. So as I said, for many, many years, we were only able to see supermassive black holes and infer their existence from when they were feeding. Okay, so from when they were accreting this material. But in fact, we think now that there are supermassive black holes at the centers of all galaxies. And in fact, most galaxies are not quasars, so they're not feeding rapidly. Most of the time, the supermassive black hole just sits at the center of the galaxy, and it's just sitting there. It's not, it's not feeding actively. It's not shining as a bright quasar. It's just sitting there. So, well, how do we know that? How do you know that there's a supermassive black hole if it's not doing anything? And the answer to that question is gravity. So I'm just going to remind everybody about Kepler's laws here. So the force of gravity goes like 1 over the distance squared. And of course, the attractive force of gravity gets stronger when an object gets closer. And so we can detect these supermassive black holes in other galaxies by looking at the motions of stars in the vicinity of that massive, massive object. So here now, the mass is the mass of the supermassive black hole, and you can look at stars moving around in the vicinity of that supermassive object. Now, for external galaxies, we only have an integrated picture of these motions. So we can't see individual stars moving around much the way, in this animation, we've got, the sun and a, eccentric body orbiting around it. We can't see that in external galaxies. But what about our galaxy? So our galaxy is a little tough. So if we want to look into the heart of the Milky Way, there's a lot of dust in our galaxy. And so what I'm showing up here is a picture of the plane of the Milky Way as seen in visible light. And what you can see is that there's a lot of dark spots. And so what do those dark spots correspond to? Well, that corresponds to regions where visible light has been absorbed due to dust intervening between us and the center of the galaxy. But fortunately, infrared light can stream right to our telescopes. We don't have the dust doesn't absorb the infrared light. It just because of the size of the particles, basically, and we can actually see directly into the galactic center in the infrared. And in fact, this has been a huge advance over the last decade in our instrumentation abilities. Now we can actually, we actually have infrared-equipped instruments both in space and on the ground with things such as the Keck telescope, and we can actually look into the heart of the Milky Way. So I'm sure Andrea showed this when she was here because this is an image that her and her group at UCLA worked to produce over a decade. But now if you look in the infrared at the center of the Milky Way, what these dots are stars. These are stars in motion around a point at the center of the Milky Way. Now this is just Kepler's laws. So I just showed you earlier. We know how bodies orbit around one another. And you can just see if you focus on this star right here. As this goes around, the movie will play again. You can just watch it over time. This image starts in 1995. And you can just watch this star. It's moving, and then it whips around an object. It whips around something. And based on these orbits. Now, this is very, very simple. This is just Newton's, gravity. This isn't anything fancy. We can measure the mass of that object based on the motions of all of these stars in its vicinity. And in fact, when you do that, you find that the mass of this object, which is also coincident with a radio source, which is called Sagittarius A star, this is the center of the Milky Way, that mass is about 3 to 4 million solar masses. So times 10 to the 6 solar masses. Now, so this should answer at least some of your question. Okay.
I don't know what the theory of these things are, but I imagine you don't have an array of statistically significant array to estimate the parameters from. So once again, this is on the basis of scattered, accumulated observations.
No. These are systematic observations that are taking place over a decade. So actually, we've been just looking at the galactic center for a decade and watching those stars as they move around a central point mass. Now, if there was no supermassive black hole there, these stars would just be going in random directions. So how do you get this star to just change its direction? So you're a skeptic. galactic, but this is the best evidence we have in all of the universe.
I'm cautious about looking at things as complicated as the center of the galaxy.
But you know what's so fascinating? So this is really simple. If you had said, 15 years ago that we were going to be measuring Keplerian orbits of stars in the center of the galaxy, people would have said, that's crazy. I mean, you can't possibly do that. And now and actually this has been confirmed independently by a European group who get a similar measurement. So that's a good question. I mean, it's sort of a few times a semester, an observing semester. So they sort of have multiple observations every year and you can see this starts in the middle of 1995 and it goes all the way up to 2006. So. No, so these are actually now, these are not extrapolated. So on some of them, you can see we don't have the full trajectory. So on this guy, we have it's almost closed. And I believe that now there's new data where it is actually, and you can just see it, if it continues on, it will close. But you can see some of these things haven't made a full orbit. Yeah, so this guy is going at around 5,000 kilometers a second at 17 light hours from the black hole. So it is kind of, it is amazing, but it is amazingly simple to understand this system. Newton knew about this. So we've actually been able to confirm the existence of this supermassive black hole, but the physics of it is actually very, 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 very simple. So we can all understand that. So what happens when stars get too close? So those stars were, traveling perilously close, 17 light hours away from the supermassive black hole. What happens when they get a little too close? Well, what happens is they get disrupted and they get ejected. So if a star gets too close to a supermassive black hole, it can actually be ripped apart by the gravity of the supermassive black hole. So many of you have heard this, kind of a picture of if somebody were to try to go into a black hole, the gravity on their feet would be so much stronger than the gravity at their head that they would get ripped apart and turned into spaghetti. Well, a similar thing happens with a star going around a supermassive black hole. This star, when it gets very close, it gets tidally disrupted, and we're all familiar with the tides, being, a few feet from the beach here. It gets tidally disrupted from the tidal force of the supermassive black hole, and you get this sort of streamer of gas. Again, this is an artist's rendition, but I'll show you an actual calculation of this. Now, Woody Allen knows all about this. It's hard to climb out of supermassive black holes and retain one's ear for music. Okay. So now that's what happens if a single star gets too close. It can actually get shredded. But what if a pair of stars gets too close? Okay, so now you have a stellar binary, and it's coming close to the supermassive black hole. Well, what happens to a binary system is that one member of the binary system can remain in orbit near the supermassive black hole, and the other one will get ejected at very, very high velocity. So you're thinking to yourself, wait a second, gravity is attractive. It's always pulling. It's 1 over r squared. If it's always pulling on stars, how does it kick them out? Yeah. Very. So in fact, it does. So this is actually very, very similar to the gravitational slingshot. So what happens here is that, for those of you not familiar with this, when we want to send satellites to the outer solar system, okay, we use the orbital motion of the planets to give these satellites a boost. So now, if the planet, this is just a case where, you imagine you've got your satellite coming in, here's Jupiter. Okay, if Jupiter were just sitting in isolation by itself, not in orbit around the sun, the velocity in would equal the velocity of the satellite coming in would equal the velocity it had when it exited. And that's just by conservation of energy. Okay? But Jupiter is in orbit around the sun. So when we send this satellite in, if we send it in at the right trajectory, it can come out at a velocity that's enhanced by Jupiter's motion around the sun. So it's taken a little bit of energy from Jupiter, and it's an infinitesimally small amount of energy from Jupiter, so Jupiter doesn't mind. And that satellite can then be boosted at high velocity, away. And this, so if you wanted to escape the Earth, so the Earth's gravity is pretty strong. Well, so first you need a rocket. That's pretty clear. And if you would need to get to a velocity of 11 kilometers a second. 11. So that doesn't seem like such an astounding number, but that's 25,000 miles an hour. So that's a really impressive amount of energy. Now, what is this escape velocity? So this is again back to Newton. This was in fact, black holes were really postulated many, many years before we actually were able to observe quasars, just reasoning based on escape velocity. So this is the formula for the escape velocity. If you have an object with a given mass and at a fixed distance from that object, the escape velocity is just given by this equation, very, very simple equation. So more massive objects have larger escape velocities, and more compact objects have larger escape velocities. So how do you get out of the Milky Way? So if you need to go at 25,000 miles an hour to get away from the Earth's gravitational potential, what do you need to get out of the galaxy? Okay, well, you need to go 100 times faster. So instead of going at 10 kilometers a second or 11 kilometers a second, you need to go at 100 kilometers a second. Okay, and that's, if you calculate the energy that translates to, that's 10,000 times more energy. So these things are going really, really fast. And people thought back in the 80s, well, if there was a supermassive black hole at the center of the galaxy, what would happen to stars going nearby? And in fact, it's this gravitational slingshot. A binary star would come by. It was actually Jack Hills who predicted this, and this is just the equation. Don't pay any attention to that, except just to know that this has been worked out. In 1988, Jack Hills actually suggested that, in fact, stars would be kicked out at such high velocities. These velocities could get to thousands of kilometers a second, which means they could actually escape the gravitational potential of the Milky Way. And that is why it's really the great escape, because this is, a huge amount of energy. These things are going at huge velocities. So let me just go over again exactly how this sort of black hole slingshot works. You imagine you've got your binary star system and your supermassive black hole. This is a very sophisticated simulation of this effect. Okay, so the black hole is constantly tugging on this binary from gravity. Okay, so it's always tugging on the member. It's always tugging harder on the member that's closer to it. Remember, gravity goes like 1 over distance squared. Okay. Now, if the time for this binary to go around, one another, the orbital time of that binary is similar to the time it takes to go around the supermassive black hole, so the orbit of the binary system near the black hole, it's always going to be tugging on one harder than the other for the whole orbit. Do you have a question? Or? Okay. Jump right in with questions, guys. So if it's, if that happens, okay, if that inner orbital time is similar to the time it takes to transit around the black hole, that binary can be tugged apart. And so by conservation of energy and angular momentum, one member of the system remains closely bound to the black hole and can actually be going in a very, very tight orbit by that supermassive black hole, and the other one gets kicked out at very, very high velocities. So it's and this is kind of a resonance effect. Okay, now you can think about this like pushing someone on a swing set. So when you're pushing someone on a swing set, if you push them out of phase, okay, they don't go any higher, right? They just you either push them off the swing or they don't actually go. And it's the same way with this binary disruption mechanism. If if the orbital time of that binary is very, very fast, well then the binary system goes around the black hole too fast to be disrupted. So it's really this kind of nice resonance when that inner orbital time is similar to the time it takes to go around the supermassive black hole. Okay, so that's a kind of simple way to understand it. And in fact, you can do a more sophisticated calculation. This is actually just a stream of particles near a central supermassive black hole. And you can see that these particles get kicked out in various directions. This is actually, the details of this calculation are a little bit different than the circumstance that I'm describing here. But the idea is the same. You can actually kick stars out from this supermassive black hole. No, these aren't binaries. This is just to illustrate how this slingshot actually works. And so people have done more sophisticated calculations than the little PowerPoint simulation I showed. So these things should be there. And in 1988, the reason that Jack Hills made this prediction was because at that time we didn't have the infrared capability to look into the heart of the galaxy. Okay, there was those movies that I showed you of this supermassive black hole. Those didn't exist, and so people didn't know if there was a supermassive black hole in the center of the Milky Way. And so they were trying to come up with ways to figure out if one was there without looking directly at it. So you're sort of looking at the galactic center by detecting objects that were being kicked out. So we did have, so in fact, people were, it's just that the technology was, early on, we did have infrared, there was sort of the early days of infrared astronomy was, kind of in the late 70s, early 80s, and people kind of just had one pixel that they would, chop back and forth on the sky on a various object. You put these infrared telescopes on optical telescopes, so on something like the Keck, so you don't need a radio telescope. That's a little bit different. The other thing that I should mention that made this discovery possible is adaptive optics. So the size of that field that, in Andrea Gheze's images is very, very small. So with most of our instruments, when we look at the galactic center, we just see a blob of light. And it was really a combination of being able to do this adaptive optics in the infrared and actually resolve these individual stars so that we could see them moving that was really the advance. And so, there wasn't sort of large format. People were still trying to, even though that technology is in the defense industry, many, many years now, it's really, it's really over the last decade that it's become kind of standard in astronomy. That's right. They're different detectors. They're infrared sensitive detectors on the same, big mirror, if that's that. So it's not like a radio dish. It's really you're using an infrared sensitive detector on the same optical telescope. This calculation was done by Mike Miraculous. Yeah. Yeah, that's right. It is. It's really nice to see how far we've come, actually. So this was predicted in the 80s, and it took us 18 years. But after 18 years, in 2005, the first hypervelocity star was discovered. So that's just 3 years ago. The first one was discovered by Warren Brown and his collaborators. It was a B star, and I'll explain that in a minute, going at 700 kilometers a second out of the Milky Way. Okay. The next two that were found, so 2005 was a big year for hypervelocity stars. So the next one was found to be going at 550 kilometers a second. This one's at 60 kiloparsecs. This one is probably from the Large Magellanic Cloud, so I'm not going to go into that one in too much detail. And then there was another one found going at 720 kilometers a second. So remember, the escape velocity from Earth is about 10 kilometers a second. So these things are really, galactic rockets. So this sort of ushered in what I call the blue period. So there's currently 17 hypervelocity stars known. So people have surveyed the sky. In particular, Warren Brown continued his search and found about 17, in collaboration with others, found about 17 hypervelocity stars. Now, all of these stars that have been discovered up to now are young and they're blue. Okay, and they've all been found in the stellar halo of the Milky Way, which means at large distances outside of not in the disk where we sit. Okay? Just to kind of go over star color, if you look up at the sky, stars have different colors. So you've got some young blue ones and some old red ones. Blue stars are hotter and younger than red stars. And this is sort of one of the foundational diagrams of astrophysics. This is the Hertzsprung-Russell diagram. This is luminosity as a function of color or temperature. Okay, and this is really a mass sequence. On the right here is red or low temperature, and on the left is hot or blue object. So those different color stars correspond to different temperatures. And the density of points on this diagram tells you how common these different types of stars are. So you can see, well, there's not too many of these blue type stars, okay, compared to the number of these cooler red type stars. So there are many, many more of these less massive red stars than these very, very hot young blue stars, okay? And if you want to know sort of, well, what are the colors of stars in the Milky Way? Well, so the bulge of the Milky Way, that's the sort of spherical distribution I talked about at the beginning at the very, very center. That's kind of old and red. It's got lots of low mass stars in it. The disk, the thin disk where we're sitting, it's got a lot of young stars because it's an active site of star formation. So there's lots of blue stars in there. And the halo of the Milky Way, the stellar halo, is sort of this very extended distribution of stars. And that's all got basically red stars, old red, less, not very massive stars in it. And it's in this, basically spherical distribution. So in this sort of early days of hypervelocity stars, which is where we are now, people have found sort of blue needles in a red haystack. Okay? All of the hypervelocity stars so far have been blue, but the whole halo is red. So it's pretty obvious why you can find these things, because if you're looking for something blue against something red, that's even with some major color blindness, you can distinguish that. But what if you're looking for red things in the red halo? Okay? That's a lot more challenging because, now you're looking for a red needle in a red haystack. Okay? And that's really difficult. But, you want to do this, and the reason you want to do this is there may be many, many more of these red hypervelocity stars than blue hypervelocity stars. Okay? And in fact, one of the exciting things that you can do with red hypervelocity stars, which you can't really do with blue hypervelocity stars, is you can see them on the rebound. So with blue stars, they're very, very young, and they have very, very short lifetimes. So they go out of the galaxy, and by the time they're transiting out, they end their lives, as in supernovae, for example. Okay. With red hypervelocity stars, okay, if they're kicked out at high velocity, but not quite enough to escape the galaxy, okay, the black hole is kicking things out at all different velocities, sometimes with, velocities of 1,000 kilometers a second, sometimes with velocities of just a few hundred kilometers a second. If the black hole is kicking these things with not quite enough juice to get out of the galaxy, we can see these guys on the rebound. So we can see them coming back towards the galactic center because their lifetimes are long. We can actually watch them as they fall back down on the galactic center. So if you look at the distribution of hypervelocity stars that have been found to date, this is just number as a function of velocity. This is zero velocity, so this is very, very high, where velocity here is now radial velocity. So this is the velocity of the stars on the way out of the galaxy. Okay, so these are our hypervelocity stars that have been found so far, and there's nothing over here. So we want to find the ones that are over there. We want to find the red ones. So
out of this massive black hole, and you know sort of where it is and how massive it is, what do you think that you learn from all of this?
So exactly. So what can you do with more of these hypervelocity stars? So there's lots of unsolved mysteries of the Milky Way that we want to address. Yeah. Yeah. There are about 17 known now. So this is an older figure, so there's only 11 on this diagram. But all the rest of them fall here as well. So So there's only this forms the bulk of the stars in the stellar halo of this is sort of the average velocity of the stellar halo. So this big peak here are just regular stars that are orbiting in the galaxy. Is that what you're wondering about? Yeah, so these are just the normal stars in the galaxy, and then, because this is just a histogram in velocity, and then these guys at very, very high velocity, you can see they're way far away from this distribution, major outliers. So these are the ones that are being kicked out by the black hole. We're looking for more wherever we can find them, but we can't find the blue ones here because their lifetimes are too short. We can only find the red ones here. So we really want to try to find more of them. And that gets at the question of, well, if you had a lot more, what do you learn? Well, so one thing that you learn is you can see the galactic center indirectly. So even though we have powerful infrared instruments and we can look in the galactic center, we can still only see the tip of the iceberg. We can only see the very, very most luminous stars in the galactic center. So I showed you that Hertzsprung-Russell diagram, and all of the things that we see are at the top of it, so at very, very high luminosity. So if we could find a lot of these hypervelocity stars, we could basically probe stars that we can't see directly just because their luminosities are not high enough. Okay? Another thing that we want to do is we want to learn more about the kicks. So we know that there's one supermassive black hole at the galactic center, and it's got a mass of, a few million solar masses. But there are different mechanisms to kick these stars out of the center of the galaxy. So I talked about this one where a single supermassive black hole disrupts a binary star. Okay? But you could also have an intermediate mass black hole. So this would be a black hole of about a few thousand solar masses. Okay, that could also interact with stars and kick stars out of the center at high velocities. Okay, so that's another mechanism. And in fact, one thing we don't have a very good constraint on is how many stellar mass black holes are in the center of the galaxy. So we know the mass of this one pretty accurately, but there's still room for stellar mass black holes in the galactic center. So let's say, there could be a population of those. And each of these different mechanisms predicts a different distribution of these stars on the sky and predicts a different distribution of these stars in color. So we really want to kind of flesh out this system. Now, one of the most puzzling things about the galactic center is that when we look, we see very, very young stars, and we see them very, very close to the black hole, so 17 light hours away. Okay? Now, it's really hard to form stars near a supermassive black hole, and the reason it's hard is because in order to form stars, you need a dense concentration of gas. That gas has to be so dense that it can allow the stars to actually form. And near a supermassive black hole, you might expect, these are called molecular clouds because they're made of primarily molecular hydrogen. You might expect that near the gravitational field of a supermassive black hole, these clouds would get ripped up. And so how can you form stars if you're ripping up, their nests, basically? So this is a major unsolved mystery in the galactic center is how does star formation proceed in the vicinity of a supermassive black hole? How do we get those young stars in the positions that we see them? And in fact, at very large distances, so early in cosmic time, we see bursts of star formation. And we think that those bursts of star formation are happening at the centers of galaxies, where there should be these supermassive black holes. So in fact, trying to unravel the star formation at our own galactic center tells us something about star formation at large distances. Another important thing about these hypervelocity stars, another important constraint that we can get, is on the shape of the Milky Way's dark matter halo. So our modern model of how structure forms in the universe is that we have the bulk of the matter in the universe is in dark matter. And if we allow that dark matter to evolve in time, this is now a simulation. This is a simulation done by someone who's in residence here at the KITP during our program. If you run a calculation of this dark matter as it evolves in time, the Milky Way, these are now dark matter particles, okay? And this is the Milky Way's halo. You can see this is running forward. You have all of these small structures which accrete into this very, very large structure at the center. Okay? One of the things that's predicted in this model is that you should generically get a non-spherical dark matter distribution. So the halo, the dark matter halo, and not the stellar halo now, we're just talking about the halo of dark matter, should have a particular shape. And that shape can either be oblate, so like a squished orange, or it can be prolate, like a cigar. We don't know what the shape of the dark matter halo of the Milky Way is. The one, yeah? Yes. Yes. So that is, that actually one of the key things about in the Sloan Digital Sky Survey, we've been able to measure the escape velocity of the Milky Way, and that the motions at those distances are dominated by the dark matter. So out at many kiloparsecs. Okay. So now, if you had a perfectly spherical halo, dark matter halo, and you have a star, and it's rocketing out at these very, very high velocities, if it's perfectly spherical, the trajectory of that star just looks like a radial ray right out of the center. But now, if the shape of the dark matter halo is somehow prolate or oblate, the trajectories of those stars will bend, because the gravity will be dominated by the dark matter, and the gravity will be pulling in a different way in this case than in this case. Okay? And so, if we could measure the trajectories of these hypervelocity stars, and we had many of them, then we could actually measure the shape of the dark matter halo of the Milky Way. So it's a pretty, yeah, do you have a question? That is a really good question. So we don't know what the dark matter particle is, but we know from the distribution of galaxies, and we know from what's called the cosmic microwave background, that there exists this component of the universe called dark matter. And dark matter, what we're made of are protons and electrons and atoms. Dark matter is a particle which we don't exactly know what kind of particle it is, and we can only, I can see you right now. We interact via gravity, but also via electromagnetic radiation, so you can see me. We can't see dark matter directly. We only know it's there because of its gravitational influence, because the dark matter particle has mass. So we don't know what it is, but we're hoping within the next decade, or maybe within the next few years, to figure that out. But that's a really good question. That's, the bulk of the energy of the universe is in what's called dark energy, and the bulk of the matter in the universe is what's in this dark matter. And the only way we know about it is by its gravitational influence on matter that we're used to, like atoms like us. Great question. So just to kind of give you an idea of kind of where this field is really right now, most of astronomy is very mature. People have been studying the heavens for thousands of years. We've got very well-developed ideas of how things form and evolve. Hypervelocity stars are really in their infancy. So they were predicted in the 80s, but the first ones have just been discovered 3 years ago. And so this field is really in just the very, very early stages. So what's next? Well, we need big surveys to find them. We really need to find more. So 17 stars is not, it's just not enough to kind of get at any of these questions that I was talking about earlier. This is just a map of, our current large survey, which is the Sloan Digital Sky Survey, which is now surveyed a quarter of the sky. And of course, we need big telescopes to learn more about them. And so in the United States, we have two main big telescope programs, the 30-meter telescope and the Giant Magellan Telescope. And in fact, California is really the heart of this international effort. The University of California is involved with the 30-meter telescope, and these are just extraordinarily exciting opportunities for us to learn more about these very, very interesting objects. And so if there are any more questions, I'm happy to discuss at length. So the way you tell it's a hypervelocity star is from its, there's two things. So from its radial velocity, if it's got a radial velocity of 700 kilometers a second, there are very few mechanisms that can even approach that type of velocity. But the way you get the radial velocity is by taking a spectrum. So I should have mentioned this earlier. So we take we take a spectrum of these stars, and we look at the shifts of their spectral features with respect to what we know in the laboratory should, those lines should be. And so this is just a Doppler shift, effectively. Yeah, so certainly if the next generation space telescope will be very, very useful, and the reason is because what we want to do is we want to get the orbits of these things. So we want to get their trajectories. Like I said, we can figure out if the dark matter halo is squashed or not once we have those trajectories. And the cameras that'll be available on these telescopes may allow us to get very, very fine measurements of those positions, because in space, with the high resolution, you can actually make very, very precise astrometric measurements, and so that is something that we're looking forward to. Yeah. So there are. So these are direct detection experiments, and so they come in various different flavors. So you want to have a very, very well-controlled environment where you have sort of detectors underground, very, very far underground, and you look for sort of these this is for dark matter that interacts very weakly with regular matter that we're familiar with, and so you look in these detectors for sort of variations as the Earth goes around the sun in different directions as it tracks through the dark matter halo. So there are these experiments. There are other types. There's a whole variety of direct detection type of experiments. So people are trying really, really hard to find the dark matter particle because the Nobel Prize isn't far behind. Yeah, so you're talking about the Large Hadron Collider. So in fact, if one of the things that the Large Hadron Collider is attempting to do is to determine whether or not supersymmetry is in fact the correct model for particle physics. And if that's the case, then there are some supersymmetric dark matter particles that may be suggested by that. And so that's certainly a potentially exciting outcome of the Large Hadron Collider. But we really need to collide leptons. Okay.
Have you found any intermediate mass black holes?
That's a really great question. So we've been looking. So there have been claims of intermediate mass black holes in smaller. So there's this really fascinating relationship called the mass velocity dispersion relationship, and that is that the mass of supermassive black holes is very, very tightly correlated with the velocity dispersion of the stellar system around it. So in our case, it would be the velocity of the bulge of stars in the Milky Way. Okay. So now if you go from supermassive black holes to intermediate mass black holes, that tells you need to go to a lower mass stellar system, so you need to go to something like a cluster. And there has been tentative suggestions that there is in fact intermediate mass black holes there, but this is all this is really early days of that field as well. So it's pretty exciting times for black holes. That's right. So this is, in that system, it really is this resonance. So if, you've got the period that they're going around one another has to be similar to the orbital period that the thing goes around the black hole. So you just imagine it like this: you've got your supermassive black hole and your binary system, okay, and it's tugging on this binary system. It's tugging harder on the one that's closer. So if this thing is going really fast, well, it's tugging on this one, then it's tugging on this one, then this one, then this one. But if this is going around at just the right speed, it's always tugging on the one. Okay? And so when you get those periods similar, it's sort of then you can actually disrupt the binary. And of course, that's a kind of simple picture. Once you add other bodies of different masses, it gets a little bit more complicated. But that's the way to think about it. Okay, so you've had your hand up for a while. Uh-huh. Yeah. Yeah.
Is there a point at which they start to blend into the background stars?
Yep. So in yes. So the thing is that they stay, their orbit doesn't change to, over millions of years. It'll stay on an orbit that's radial from the galactic center, whereas these other stars are moving more, kind of isotropically in all directions. And so that's, relatively short. That's right. So we can actually distinguish things that are being, even if they don't have enough oomph to get out, we can actually distinguish them. In fact, in our most recent work, we found 5 candidate red hypervelocity stars on the rebound, and we were actually able to rule out 2 additional ones because their trajectories were not consistent with coming from the galactic center. But it's very, very hard to get the orbits of these things, so that's why we need the new data. Yeah. Well, so this is another issue that gets back to that star formation question. So we think that at high mass, the binary fraction is very, very high. So the number of stars at large, sort of these high mass blue stars, we think that the fraction of those systems that are in binaries is very, very high, approaching 100%. And we don't actually know what the binary fraction is at lower masses. So it ranges from 50% maybe to it can go higher. So we'd like to know what the binary fraction is at the galactic center, and that's why we need to compare detailed models with sort of the observations of these stars. So it seems like, what happens in these triple systems is that usually you get a binary and the other, sort of threes are crowd in stellar dynamics. So you can have, so you have, like, for example, the solar system, right? You've got the sun and you've got, multiple bodies. But with stars, I don't believe we have any kind of, I don't believe we've observed any. Well, that's not true. I think that there is an observation of a stable triplet, but they're not, they're not extraordinarily common because it's a very unstable configuration. No, this is a purely classical problem. At the distances that we're looking at, it's really just Newtonian gravity. So there's no influence of the metric being. Yeah, it's a point mass. Nowhere near the speed of light, and nowhere near the distances where the actual space-time variations matter.
It looks like that one orbit around the galactic black hole might be close enough to start precessing.
So that's something that group, so the 2 main galactic center groups are actually thinking about, looking for, over time. Of course, it takes, so it's just on one loop. So, now you have to look for precession, and it is a difficult measurement to make. But certainly, people are thinking about exactly those types of observations in the future. So people like Andrea with Keck and the group in Europe with the VLT. So this is something that people hope to see these higher order effects in the orbits once they have more data to probe that. Oh, sorry. Well, yeah, those are all in the halo. So we know that because of their luminosities, we know their distance. Well, so far we haven't found, we found these candidates, which I just mentioned, which were closer to the center, but nothing at the galactic center. So they're very quickly kicked out. Yeah, they're in the halo. That's right. Yeah. Right. So. So it's conservation of energy and angular momentum. So the one star, so you have this, the orbital energy. It's basically like you've got this system that's coming in at infinity with, the velocity that's associated with the supermassive black hole is, 1,000, depending on the mass, but, maybe it's 1,000 kilometers a second. If you just take the gravitational potential energy and ask what the kinetic energy of a test particle is there, okay? Then you've got the orbital energy of the supermassive, of the binary. And that's sort of order a few hundred kilometers a second. So maybe, 100 or 200 kilometers a second is the speed at which those guys are rotating, right? So then the actual velocity that the thing gets ejected out is, you can think about it like, sort of a geometric mean between that gravitational binding energy and the orbital, the original binding energy of the supermass of the binary system. So what's happening is that you've got one system that's bound, and it comes near the supermassive black hole, and the potential energy near the supermassive black hole is large enough to be, it's much greater than the binding energy of that binary system. So it breaks up the binary, and then one member of the binary becomes bound, so it becomes bound to the supermassive black hole. And the other one, because you have to conserve energy and angular momentum, the other one gets kicked out with the residual velocity, right? Because now this thing, this thing is now going, very fast, but now it's bound to the supermassive black hole. You can think about it. You can think about it that way, and it really is just this simple energetics argument. It's not quite, it's not quite the same exact, it's not quite that principle because, when like if you had a yo-yo that and then you just cut the cord of that, so it's not exactly the same, but that's right. So the energy of the energy near the supermassive black hole is enough to exceed the binding energy of this. Mm-hmm. That's right. So in fact, when people first saw that S02, which I showed in the movie, they said, "Oh, the only way to get a star there is to have a binary disruption, to have a triple system." So that's.
Wrap up there. I'm sure that if you have questions afterwards, then we'll be happy to talk to you privately. But let's thank you again for a very